Okay. So, and today we will start here with or continue with the chapter polymorphism. Then you are just clicking here, and then you have here a small description what is meant by polymorphism. I will now not go through this because I told you this a few weeks ago. So when if we are talking about polymorphism, then we are talking about minerals which have the same chemical formula or the same chemistry, but we have, due to changes of pressure and temperatures, we are dealing with a different crystal symmetry, yes? And I showed you all these figures using quartz, yeah? And there the quartz has different modifications. I mean, here on the Earth's surface, you will find the alpha quartz, and the alpha quartz, that is just hexagonal, yeah? It shows this hexagonal shape from above. So another polymorph mineral that is, for example, the diamond. At low pressures, you have the graphite, and at higher pressures, you are forming then the diamond. And the graphite, that is actually the softest mineral, and the diamond is the hardest mineral, and they are all made up of carbon. So other polymorphic mineral, I think Neil has shown you or started this week in the lecture with this calculation from the alumosilicates, yeah, is it? So in the alumosilicates, these are also polymorph minerals. All three varieties of them has an Al2SiO5 chemistry, but they have, due to changes of pressure and temperatures, the volume will change and the density will change, and therefore you get these three varieties, and one is the high pressure modification is called the kyanite, the high temperature modification is called the sillimanite, and at lower pressures and low temperatures you have the andalusite, and there Neil is just doing now with you in the practical the calculation of the stability fields of these three alumosilicates. So then here you can just click on page down, yeah, and then you have some other descriptions. So, and if you are going through all this, yeah, then that is actually a huge help. But we will go now here to continue. So, and here we have our we have here several tetrahedrons and octahedrons, yeah. Maybe we can even make it bigger here while we are moving with the whole stuff to this side. Does it become bigger? Not really. And here you have then again some animations. We have the displacesive animation, yeah. Here we have, for example, the quartz, yeah. So, and I showed you last week or a few weeks ago all this arrangement of the different tetrahedrons using the different quartz varieties. So, and this is the arrangement of the high quartz here. So, and here you have some descriptions, but that is not, you can go then through by yourself because I have told you this in class now a lot of times. Now here we have the arrangement of the tetrahedrons in the high quartz modification, and now we are going to the low quartz modification. Yeah, again, high quartz, low quartz. So, and then you can see that the tetrahedrons are just switching their position. Yeah. So, if we are talking about a high quartz, it is a quartz modification which will be formed at higher temperatures. So, and that means if we are increasing the temperature, then we are increasing the volume, yeah? The easiest example is always the system of water. You have ice, you have liquid, and you have steam, yeah? That is the easiest example. So, and if we are checking here the low quartz, then the low quartz is more shows a lower disordering structure. So that means that then the volume becomes smaller because we are dealing with lower temperatures. And if we are going now a step further, then the high quartz has a higher entropy as the low quartz. Yes, I introduced you also 2 weeks ago the entropy, and Neil is now doing these calculations using the entropy. And the entropy that describes the disorder of a mineral or phase. So if we are increasing the temperature, then our rate of disordering becomes higher. Easiest example again, we are cooking water or water boiling at will boil at 100 degrees Celsius, then we are making steam out of our water, and then the entropy becomes higher because the rate of disordering of our atoms becomes also higher. Yeah? So and if we are increasing the temperature, then we are increasing the entropy and we are increasing the volume. So, and you must only always remember the system of water, because I mean, if you are boiling then or cooking the water, then we are increasing the volume dramatically as well as the entropy. Yeah? So, and now we can go here just previous and go into the reconstructive animation. So, and here we have also a lot of tetrahedrons, and we have here the SiO4 tetrahedrons, and then let us just check. We have here the movie. So here we are also changing always the positions of our tetrahedrons. So, and that is also for quartz variety, but here we are not going from low quartz to high quartz. Here we have the very high temperature variation from tridymite and cristobalite. So, and here we are just adding some tetrahedrons while we are increasing the temperature. So, and here we have something about polymorphic systems. We have here the carbon, we have the quartz, and we have the K-feldspar. So, carbon, I just told you that is the diamond. Yeah, you have the carbon and the diamond. So, and here we have there the phase diagram. Here again on the x-axis, we have here now on the x-axis the pressure, and here on the y-axis the temperature. Therefore, you have always to be careful. Yeah? Just checking at first this diagram where the authors made or put the pressure and where the temperature. So, and then you have here, that is in kilobars, 600 kilobars, here we have 100 kilobars, here at the Earth's surface, and then you have here the stability field of the diamonds. So, and here we have 100 kilobars, and this the first diamonds can be formed at a pressure of about 60 kilobars, yeah, that is then here. So, and if you are, while we are running on the x-axis here, we are just going inside into the Earth's mantle, yeah? So, in the stability field of the diamonds, or the diamond window, that is actually then at a depth of about, ranging between 175 and 220 kilometers. There we are just sitting. Here we have 100 kilobars, then we are sitting here in a depth of 300 kilometers. But the important boundary, that is this boundary here, so that means at lower pressures we are forming graphite, and at higher pressures we are forming diamond. Yeah? So that the thing what you should have in mind as an ES203 student, that means the diamond is the high pressure modification from the graphite. So, and if the diamond came up only very slowly to the Earth's surface, or if the oxygen fugacity is too high, we will talk about this the next year in ES301, then the diamond goes back to graphite, yeah? So, but if it comes very fast to the Earth's surface, though there is no time left for for the transition into the graphite, then the diamond can reach the Earth's surface as a stable mineral, yeah. So, and then you can connect it and put it on your finger, yeah. So, if we are going then at temperatures here again, Kelvin, therefore you must always be carefully if they are using degrees Celsius or they are using Kelvin. Yeah? Kelvin comes from the American system, Celsius comes from the European system. So, but anyway, if you have a temperature of about 4000 Kelvin, which is then about 3700 degrees Celsius, then you have here vapor, and here you have liquid, yeah? And here you have another carbon modification, which is called carbon-3. So now we are going to our next system. So here the mineral name, here we have now the diamond structure, yes? That is again, this stick and ball model, what I showed you last week, that is the diamond structure. Here we have a perspective view, here we have the top view. Yeah, that is just, if we have the top view, then we are looking from the bird's eye, yeah? It's always then from above. And if we are talking about crystallography, yeah? If we are talking about crystallography, then the bird's view is always this. These are our three axes in the room, yeah? So that is then A, B, C, and then this one is the bird's view, yeah? And the perspective view, that is then always along A. So now going back, then we are just checking the graphite, and the graphite shows totally different, yeah? The atoms are totally different arranged in the graphite, and if you are checking the density of the graphite, and the graphite has a much lower density, and the volume of per 1 unit cell is bigger than those of the diamond, yeah? So here again the perspective view, that is then here along A, and then we have the top view that is along C, and then it looks like this. And here at the top you have always written the crystallographic class, and the crystallographic class is then, I will tell you then how it works with the crystallographic classes in the next chapter here. So, and then we can see here liquid is nothing, there is nothing. Then you can just go here back and going here to the SiO2, and you know this diagram by now as well. It is just the axes are flipped, but I gave you also in my PDFs, yeah, the stability or the phase diagram of the quartz. So then we have here the low quartz, here we have the high quartz. Here we have the trinamide, here we have the high cristobalite, here we have again liquid, then we have here the coesite, and here we have the stishovite. And the stishovite, that is then actually this quartz modification, which you can find in the Earth's mantle. So then we will now click again on these things. Here we have the low quartz. So, and that is how the low quartz looks like. And you have all these pictures in your PDFs. So we have here the perspective view, and here we have again the top view, yeah? Then we can just check the coesite, and you can see now if you are checking if you are looking at the arrangement of the tetrahedrons in the coesite, then they are packed much closer, yeah? And that is due to the increase of the pressure, yeah? Here again the perspective view, then we have here a side view, and the side view that is then along B, yeah? So then we are checking the stishovite, and there it must really be packed. So then here we have the arrangement of the tetrahedrons, but now the tetrahedrons are packed now in such a way that you have at the top a tetrahedron and at the bottom, yeah? I showed you this last week, then you can pack it or squeeze it even much more, yeah? Perspective view, top view, yeah? There you have this arrangement that the tetrahedrons are put together. So, and then we are checking just the high quarks here, and there you can see that the tetrahedrons are much more apart from each other, yeah? So, and that is just because of increasing temperature, yeah? Perspective view, top view. So, and I would, all of you should get from Neil this CD, yeah? So, and then I would suggest that you can go around through all the things and through all the description. I think that is a good preparation for the examination when you also studying the PDFs. Yeah, I told you for the test, not the examination, but for the test now, which we will write in the field. You should study these 3 PDFs, yeah? So, and here module 1 of this one is just a good reading for it. So, then we just checking the K-Feldspar. We discussed also in the class the K-Feldspar. You remember this diagram, yeah? Here we have the Albite, here we have the K-Feldspar, and then you are running along this curve. Here we have a visibility gap, and on this side we will form an Albite, and on this side we will form a K-Feldspar. So, and the K-Feldspar has following modification. We have the Sanidine, we have the autoclass, and we have the microclean. So on this side, from the albites, we have the monalbite and the albite. So, and the thing is, if we are increasing here the temperature, then we have a change of the aluminium 3 plus in the tetrahedral, on the tetrahedral side of your feldspars. So, and I told you, you can replace or you can put some aluminium on the tetrahedrons here. So, and the aluminium is a smaller bubble, so the aluminium will fit on the tetrahedrons and on the small octahedrons. Yeah, these are these Al3 plus exchanges. So, and therefore you will also change the crystallographic symmetry. So here we have, for example, the K-Feldspar, and we have here the arrangement of different atoms. We have here different atoms. We have here atom A, and we have here atom B, and then we have here just a number then with 1, 2, 1, 2, 1, 2. So, and this shows that we have a composition of 50% of atom A and 50% of atom 1. Now we will check what's happened here. So, and now we have replaced the things. We have now atoms 1 and 2 next to each other, and here we have 2 white atoms next to each other. That means we are just changing our crystallographic arrangement with the different atoms. So, and then you can see if we are changing here, if you are making here exchanges, replacing, for example, silica by aluminium, then you are changing the symmetry because of the different size of the atoms. So, and here we have now on one space we have both atoms, yeah. That is then if you have sitting on the tetrahedron, then aluminium, on the next one silica, and so on. So, or we are changing them just halfway, yeah? So we have now on every side, we have 50% of atom A and 50% of atom B. So, and if you are doing these exchanges, then you are disordering on an atomic scale, and therefore you are changing the symmetry. So that was this. Then we are coming to polytypism. So we have now here again the description, but I will not go through because we have done this before also very much in detail. But for yourself and for your own studies, you can just go through all these descriptions. So, and this polytypism that can be seen in the micas, yeah, and we have done this here on the board, the 3-octaedric micas and the d-octaedric micas, and I showed you that the d-octaedric micas, they have a space. So the M1 space is empty. So, and the next thing with the micas is you have these micas where you have potassium or other big atoms in the interlayer. There's this interlayer, you remember, the micas have this TOT structure, then interlayer, then the next TOT structure. So, and here we have the situation that the tetrahedral sheet is here in a 3-octaedral, is linked to a 3-octaedral sheet. And here we have everywhere oxygen, and they are sharing here the oxygen. So what one can see here they are here we have tetrahedrons and octahedrons, and then they have here the OH, and here they have the oxygens, yeah? So in this OH group, I mean the micas, these are hydrous minerals, and you have always on some corners you have the oxygen, and this oxygen is then here arranged around one OH group. Again, here we have the OH, and this OH is then surrounded by 6 oxygen. So here again, we have here the shift vectors. Here in the middle you have the oxygen, the OH, and here you have the oxygens. So, and that is the situation, how the different oxygens are then related to each other. So, and these are just from different views. And that we will discuss then, how these views are coming together. We will discuss them when we are talking about crystallographic systems. And the room groups. So, but for now, you as 203 students, you should remember when I'm talking about, or when I'm asking in the exam or in the test what is polytypism, then you should know that is when they are sharing in the micas, for example, how the oxygen and the OH group is related to each other. Yeah. And these are just the different room groups, yeah? Then just the orientation from your vector will change. So, and here you have the O's, that is the octahedrons, then you have the TO, that is the tetrahedron octahedron here, yeah? And here we have finally the TOT structure, which we can find in the micas, yeah? So, and here we have then the generic unit, and this is the smallest cell, that is our unit cell, and if we are doing some thermodynamic calculations, then we are and I will give you, or Neil will give you a volume, then it is always about 1 unit cell. So, and that is just how you can stack them together. Then it goes here, 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 here. And here again, the different groups. And at the corner, you have then always the oxygens, and in the middle, you have the OH. So now these hexagon rings or elements are just put together in another direction. So which makes then the room group, but I will not discuss now too much about the room group, because we have by now not started with this. So here the vector is now always changing. So and then making it once more exciting. Here you have the sheet silicate, yeah, that's a lot of micas here, yeah. So and if you are checking here, you can just view it from different perspectives, yeah. Then you can see all these different sheets. Yeah, just we are starting here and give it around. You can even put them away with your fingernail. Yeah, Echolite is always a good rock. Yes, here is very nice example. If you are checking here, then you can just remove it. Yeah? So because here that we can even make it in smaller flakes. So and then you can see the different sheets. Yes, you are starting maybe with this one here, yeah. Here again, if you are looking from this perspective, you can see all the different sheets. And they are very, very fine and very, very thin. And you can even lift them. And remove them, yeah? So, and these are just the arrangement of these different blocks. So, and then it depends just how they are arranged. So here the vector is always flipping, yeah? So in this arrangement, that is then always also a result of different pressure and temperature conditions, yeah? So now let us check what the vector is doing now. So now it is flipping in this way. That means one time the OH is sitting there, then the OH is sitting there. That is then just the movement from your OH unit within all these different sheets. And the last one, then it looks like this. And here you have then the exact description, but that is for now too much, because they are using things which we have not discussed by now. So, and here you have all of them together. So then we have here the solid solution mechanism. We have done this by now as well. Therefore we can just jump over. So these are just the different exchange vectors. Here we have the substitutional solid solution. So we have here simple cationic substitution. So in the simple cationic substitution, that is, for example, the iron-magnesium exchange. Yeah? There we are just exchanging two cations. And for example, if we are talking about the olivines, we have then at high temperatures the magnesium-rich olivine, at lower temperatures the iron-rich olivine. So, and here we have now some illustrations. So we are exchanging then just cation A with cation B. So we have here A and we have B before these atoms has been read, yeah. These bubbles are here, that is the oxygen. So, and that's this simple cationic substitution, that is the best example, is the iron-magnesium exchange. So, and here we have the compositional bars, yeah, and here it is just written what I told you. These are the two olivines. Here we have the forsterite, here we have the firelite. The firelite can have 100% iron, whereas the forsterite has 100% magnesium, and then we have here the solid solution between. Yeah, that is just how many iron and how many, the ratio between iron and magnesium, and we have done this. So, and that is the complete solid solution series here, and then we can make a partial one. Here, for example, in the feldspar system, we have here the albite and here we have the K-feldspar, but here between we have a gap. So, and here you have also written what's the radius of the cations are, because you can only replace cations with another cation of nearly the same size. So then we have such a compositional diagrams. We have also done this in class. And here we have the olivine series and the pyroxene series. And we will just start with the olivine series. So here the order describe actually four types of olivines. We have discussed in class the two end members, forsterite and firelight. Yeah, these are just here on this bar. Yeah, that is the iron-magnesium exchange. But here, if we are adding calcium, then we have here the montigilite, and the montigilite, that is an olivine which occurs together, which occurs in kimberlites. That means kimberlites are these rocks which are bringing the diamonds to the Earth's surface. And here we have the kirschstenite, and there we have once more the magnesium-iron exchange between these two end members. So these are then the olivine series. Then we are going to the pyroxene series. No, we are, yes? So, and here the order describes all the different pyroxenes. I told you the formulas for the enstatite or the ferrocylite on the board, yeah? These are the orthopyroxenes. Then we have here the clinopyroxenes. We have here the diopside. Here we have the Hedenbergite. These are the clinopyroxenes. I have also put all the all the formulas on the board. Here, for example, the order put in an orgite. Yeah? In this range we have the orgites. And during our field trip you will also see more orgites than you have ever seen in your whole life. So, and here on this side we have also the pigeonite. And the pigeonite is just a calcium-bearing orthopyroxene. And here on the top we have then the wollastonite. Yeah? So, and now we are going to the rhomboedric carbonates. So carbonates, you know by now, these are not silicates. And here we have the most important carbonates. We have here the magnesite, we have the siderite, we have the ankerite, and here we have the dolomite. And here at the top we have the calcite. So what we discussed also in class in our last few weeks, the dolomite and the calcite. So, and then we are going last not least to the rhomboedral carbonates B. So then we have here the magnesite, that is a magnesium carbonate, and we have the siderite, the iron carbonate. We have here again the iron-magnesium exchange, and here on top you have the rhodochrosite, and that is a manganese carbonate. So, and here if we have such a thing, that is then the immiscibility gap. That means there is no carbonate or no carbonate exists on this planet plotting inside this field. Yeah? You have by now seen also a lot of triangles with the immiscibility gap. So here we have, what do we have here? Yes, that is then the X-ray, peak. I showed you this picture where you have it also on your PDF. Why they have used the X-ray to figure out that this mineral which I showed you there is a beryl, yeah? And I mean you have here then the crystal. So that is your crystal here, something like this. So and then you have here an X-ray. So and then you have here a film, yeah? So then you have here such a film, and then you are getting different spots on the board. Yeah, I showed you this in one of my slides. Yeah. So and then these spots they have here. there's a distance between all these spots. These spots are actually not the atoms, these are the shadow of the atoms. So, and then you have here the distance between all these spots, yeah? So, and that shows then, if we have Mg2 or if you have a magnesium-bearing olivine, then the distance between all these spots is smaller, yeah? Because the bubble is bigger. So, and if you are replacing it with iron, then the distance between the spots become bigger. So then we have the coupled cationic substitution. Moment. So, now we are going here to these coupled cationic substitutions, and we have done the coupled cationic substitutions. These may have been, for example, the Chaumag substitution, yeah? We have the magnesium Chaumag, the iron Chaumag, and the calcium Chaumag. So in the magnesium Chaumag, for example, that was then, we are replacing magnesium plus silica with 2 aluminiums, yeah? Then you have here 6 atoms in the outermost ring, and you have also 6. So in the iron Chaumag is just iron plus silica replaced by 2 aluminium, and then you have the calcium Chaumag replaced by 2 aluminium. So now we would like to know, or at least I think you maybe like to know it, how this looks like from the bubble's perspective. So we have here at first the schematic illustration, yeah. Here we have 2 atoms, 2A will replace atom B and C, that is the situation here. So, and here we have again the oxygens, and here you have your atoms inside, the cations. Again, yep, here you are replacing them now. So that's all. So and then we made, that is the schematic illustration. Then we have here a coupled substitution. So and here they are not using the Chaumag substitution. They are using here the calcium-sodium exchange coupled with no, we have here, what do we have here? We have here the pyroxenes, yeah? We have here a jadate, and here we have the diopside. So, and if we are making from a diopside and jadate, yeah? And if we are talking about eclogides, because I saw just now on your screen the eclogide, then we are moving to higher pressures. If we are making an eclogide, and then we are changing, or we are going from a diopside to a jadate. So, and here we have this example from the diopside, and here we have a between the compositional gap. But as I told you also before, if you are increasing the temperature or the pressure, then you can close these gaps. Now we are checking how it looks like from the plagioclases. We have here also sodium-calcium substitution. And then we are going from the albite to the amortite. So, and now the plagioclase solution. Yes, you know this diagram by now as well. You have it also in your folder. The K-feldspars, the albites, the anortite. So, and here you have these three temperature lines, at 900 degree, 750 and 650. And at 650 you have here this compositional gap, the immiscibility gap. So here now the temperature effect on solid solution. Here we have again our diagram from the K-feldspars or from the feldspars. Here 100% albite, here 100% K-feldspar. If we are going down with the temperatures, depending on the composition of the melt here, then you can form here an albite, you can form here both, and on this side you will then form the K-feldspar. So here now something to the temperature composition that is for the alkali feldspars, and now we are going to the feldspars. So here they have now made this cake. And here you have the liquidus surface that is just from, that is a three-dimensional picture. And here you have the different temperature lines. And if you are going down, then you are reaching this surface here from the diagram which I showed you before. So, and here we have the same thing between the albite and the anortite at different temperatures. And here in this field, you have the solid solution. That means you have here the liquidus, and here you have along this curve, you have here the solidus, yeah? And you know by now also what the liquidus is and what the solidus is. So here that is then here just, this is this surface, moment, this surface here, on this side, that is this surface, and this surface here, that is this surface, yeah? And here this one, yeah? That is here the miscibility gap. So, and if you are increasing the temperatures to 750 degrees, or 900, then the miscibility gap is away. Yeah? So, and if you are measuring with a microprobe your feldspars, and then you are calculating the X albite, X anortite, and X K-feldspar, Neil has done this with you last week in class, yeah? The triangle, and then you are plotting the minerals inside, yeah? And if your mineral composition is then plotting somewhere here, then you know this feldspar was formed at 900 degrees Celsius, yeah? So these are very easygoing things. So, and if you are dealing with igneous rocks, then it is even much more easier compared to metamorphic rocks. For example, when we are going to Coro and we will be there in 2 weeks, yeah? In 2 weeks we will just walk around there, and then you will see thousands of basalts. So, and all these basalts, they containing plagioclases, yeah? Where some of them you can even see the white needles of the plagioclases, yeah? So, and then one can just measure this with a microprobe, and then you know at which temperature at least this feldspar was formed, or this plagioclase, yeah? So, because if we are talking about igneous rocks which are intruded at the Earth's surface, then the pressure is atmospheric pressure, yeah? So, and then you can do this calculation just using 1 bar or 1 kilobar, yeah? That doesn't matter. But if you are talking about metamorphic rocks, and you will also see some very high-grade metamorphic rocks in the Coro, you will see them actually at the first day, you will find these spinel lersulites. And they are coming from the Earth's mantle. So when they were transported or brought up with this magma, which you can find at the Earth's surface, yeah? But this magma or this basalt or andesite, this magma, cooled down at the Earth's surface, yeah? Therefore the pressure is 1 bar or 1 kilobar, doesn't matter, yeah? So, but the spinel lersulite, which was brought up with this magma to the Earth's surface, the spinel lersulite was formed in the Earth's mantle. So, in the spinel lersulites from Koro, they formed in a depth of about 90 Ks, something like this, yeah? Some of them maybe only 40 kilobars, yeah? No, not 90 Ks, 90 kilometers. Now it's correct. No, I'm running now, driving now. So then they formed in a depth of 90 kilometers. So they formed in a depth of 90 kilometers, that is quite deep, and one has still to figure out if these are fertile lersulites or depleted. I gave you also this diagram in class, you know, this cross-section through the upper Earth's mantle, yeah? And there is written then the fertile lersulite and the depleted one, and the fertile lersulite that is then just formed from recycled crust, yeah? So that means you will find them a little bit more potassium group elements inside. But we will discuss this then in the field, and I will take all these things, with even this one, with us to the field, and we can just check where we are sitting in nature so that you can compare all these diagrams with the observation you are doing on the rocks there. Yeah? So, and now we are doing the same with the pyroxenes here. That these are now again our pyroxenes, the N-statite, ferrosilite is pigeonite, dioxide, Hedenbergite, and here we have our orchites. And these orchites we will then also find a lot of them, or you will find a lot of them. So, but anyway, we have here now this cross-section. So how does it look here? So that is then, here we have the orthopyroxene, the pigeonite and the orchite, and here between we have the miscibility gap, yeah? And this one here is the miscibility gap, this one, yeah? This black one. There is no pyroxene on this planet which will plot inside here. But you can check these orchites, and these orchites in these basalts are of this size. So, and then one can check if one can find the pigeonite, and then you have a thermometer. Because one knows from experiments at which temperature such an orchite is formed, yeah, depending on the chemical composition. If the orchite has more iron inside, yeah, then it is formed at lower temperatures, whereas if the orchite has more magnesium inside, then the orchite is formed at higher temperatures. So, these are always these exchanges. So, and then we have no solid solution. What do we have here? That is all not that good here because it is very, very dark. And here we have only sulfides, and that we must not discuss about now. Let us just check if the next slide is better. Yes, here we have the minerals in the potassium silica series, And here we have again such a diagram. Here we have melt, here we have our peritecticum, here we have the eutecticum. So, and we have discussed, or I showed you also a couple of this kind of diagrams. So then we have here the interstitial solid solution. What we have here, here we have again the beryl, and the beryl, you know, that is a ring silicate, and here you can see all the different rings, yeah? And it is hexagonal rings. So, and that is then the silica here in yellow is sitting on the tetrahedron, so the beryl here on the octahedron, and the aluminium is sitting as well there. And we have some vacancies between. That is then just a space left. So then we have an H2O rich beryl. So, and then we are putting the OH inside, and the OH is then sitting on these vacancies, yeah? If we are just going back, here we have the beryl, and here we have everywhere the vacancies. We are putting H2O inside, and the H2O is sitting on the vacancies. So, and that is then just the view from the z-axis, that is the bird's view, yeah, again. And here we have the view along the a-axis. So, and now we are making a sodium-rich beryl, and the sodium is then also located, sodium and lithium is then also located on these vacancies, yeah? So, and again, the bird's view. So, and that was now the interstitial solid solution. Then we have the omission solid solution. What we have here, then we have here just an iron sulfide. So, and here we have also a vacancy. So, and here you can then put on your vacancy additionally an iron. So, and that is then because, or due to the fact that you have iron 2 plus and iron 3 plus. So, and if you are if you have here 3 iron 2 plus, then you will have not a vacancy, but if you are putting instead, putting instead of this 3 iron 2 plus, 2 iron 3 plus, then you have one vacancy because of the electron balance. So, and we have also discussed such how is it called? Such omission solid solution while we were talking about the d-octahedral and the 3-octahedral micas, yeah? So, and then we have the X solution. So, in the X solution, I will also show you all these solution things then under the microscope. So, the X solution you can also see in this ultramatrix stuff from Coro. There you have X solution lamellas from one mineral in the other one. Here you have again a miscibility gap, yeah? So, and if the mineral is formed at higher temperatures, then you have here a mixture, and if you are cooling it down, then you will get such X solution lamellas, and we have done this also in class. A good example is the pertite and the antipertite, yeah? These are the K-feldspar X solution lamellas in the plagioclase, or the plagioclase X solution lamellas in the K-feldspar. And I will show it to you also then under the microscope. So that is here just a schematic cross-section. Here you have again your gap. So and here when we are going to this place here, then we have here a mixture. So and here we are running on this side along. And here we are just somewhere between. But you cannot have a mineral with this composition here. You can have one here at higher temperatures, or you are running here on the along here along this curve. So, and if you are talking about a microscopic observation, then this exsolution looks in following way. Here you have your mineral, and then you have your exsolution lamellars inside. Yeah? These are very thin lamellars. So, and then you can measure the diameter of these lamellars, and if the diameter if they are very, very narrow, yes, that tells you then that the uplift to the Earth's surface was very fast, because they occur then in a frozen stage. So, and if they have time to grow, then they are more white. So, in these exsolution lamellars you will create while you are running from a composition like here on this curve, yeah? So, and then you are getting these exsolution lamellars. So, and then you, of course, you can measure the chemical composition from here and the chemical composition from here, and then you can measure with Photoshop or ImageJ or whatever for a software. You can measure the area here in square millimeters and the area here in square millimeters. Then you have the composition here and the composition there, and then you can recalculate the composition what these both minerals had maybe here. Yeah? Then that was the exsolution. So, and then we have graphical representations. Yes, these are just the triangle diagrams. And this is such a triangle diagrams, and I showed you also in class a bunch of triangle diagrams. The CMS and the MSH, if I would be you, I would study them very carefully, because there I have some questions. So these are the triangles, and that is then the ternary system. We have ternary systems and we have binary systems, and we have here the chemical graphs, and these are binary systems. And here we are talking about the alumosilicates, which Neil is just now doing with you in class. So these are the alumosilicates containing of two components, that is SiO2 and Al2O3. Then we have here the salt, for example. We are containing of sodium and chlorine. These are just ternary diagrams. We have here the calcium carbonate. These are also ternary systems between calcium and CO2. And then we have the SiO2, and that is the quartz. So now we are done with this chapter, and that was actually just to go some of the important things to mention it once more. So, but now we are talking about something new, and these are the crystallography. So, in the crystallography is actually a thing which is taught by now not too much at universities, only actually in mineralogy classes, but the crystallography is something very interesting, and it is something very easygoing, and it helps a lot when we are starting then to do microscopic work. Because the thing what you are seeing under the microscope is just reflecting for 100% the crystallographic conditions. So, and if we are talking about crystallography, then we have the symmetry operations. So then we have the symmetry operations, and the symmetry operation that can be seen in two-dimensional pattern in the external form. That means that is the morphology of idealized crystal models. The major part of the graphical program that follows illustrates the evaluation of total symmetry content of a crystal. The symmetry operation include, we have rotations, then we have 6 rotations, and these are the crystallographic classes. Then we have roto-inversions, that is then just 1, 2, 3, 4, 5 with this line on the top, yeah. And then we have mirrors, and we have a symmetry of symmetry, a center of symmetry, and we have inversions. So these are the crystallographic operations. So, and I would also study carefully this chapter, because that can be from these symmetry operations and all these things, I can actually make a hook for you in the examination, because these are very easygoing things. So now we are starting with the rotation axis. These are these ones. So now we are dealing with two-dimensional and three-dimensional rotations, and we have combinations of rotation axes. So here we have now such a figure, and you can use figures in which you are using every day, and you can making some symmetry operations. So here we have now different figures, yeah? We have here such a flower, one-fold, then we have a two-fold figure, a three-fold figure, a four-fold figure, and a six-fold figure, yeah? And such a six-fold figure, a typical, that is, for example, an ice crystal, yeah? You can find it in the fridge. So now we are starting with this one-fold. So here we have our flower, and the one-fold rotation, that means we have to move this flower 360 degrees that it overlaps itself, yeah? So let us just check. We are just moving it, yeah? So, and then you have to move it 360 degrees that it overlaps itself, yeah, that you can produce a tally, yeah. That is a one-fold rotation axis, and that is now the first crystallographic symmetry what you have seen. Now, so, and here it's once more repeated, you have to turn it 360 degrees till it overlaps itself. So now we are going to twofold, and I'm sure that you know what happens now. That is a twofold axis or rotation, and that is the sign for a twofold rotation, yeah? So because here you have now not turned it 360 degrees, that it overlaps itself, you have to turn it by now 180 degrees. So you can turn it 2 times that it that it overlaps itself. Here it is seen. So now we are turning it 180 degrees, So we have now turned it 180 degrees and it overlaps itself. So now we are turning it again, another 180 degrees, then it overlaps itself. So that is a two-fold rotation axis, yeah? So, and that is then the same thing what you can observe under the microscope, yeah? Some minerals, you have to turn the table 360 degrees that it overlaps itself. Others, you can do it 2 times, yeah? So that is the two-fold axis. So now a 3-fold, and you know it by now by yourself, you can do the whole thing 3 times, yeah? You are just moving it like this. 1 time. 2 times. 3 times. So, and that is, then you have a 3-fold rotation axis, and that is the sign that is just a triangle, yeah? Because the triangle you can also move 3 times 120 degrees, that it overlaps itself, yeah? So, and there we are putting inside in our crystal, if this would be a crystal, you are putting then a triangle. So now we have the 4-fold axis. So when you know by now what happens, we can just turn it 4 times, yeah? So, and these are the 90 degrees. So, and then the sign of our 4-fold rotation axis, that is just this cube. So, and you will wonder, because how can one use this in practice? With this stuff you can really make money. So, because in the wafer industry, so you know the wafers, the chips, not the potato chips, I mean the chips inside the clocks and in all the electronics. So, and these chips are all crystals, but they are not sampling in nature the crystals, they are growing it in the lab, yeah? So, and then you can, and therefore it is very important, because these chips, what they are producing, they must be perfect, yeah? There you don't like to have point effects, and you don't like to have other elements inside. You like to have a pure chips in a perfect condition, yeah? So, and therefore, and this is actually the work from crystallographers. So, and therefore you need perfect chips, because these chips later on, you will mask them, yeah? So, because you are using them for electronics, and therefore the electrons has to be moved around on your chip, and there you have to mask them. And therefore they must be in best conditions, because you are getting then otherwise always defects, yeah? So, and if you are growing crystals, then this has, there are different methods to grow crystals, yeah? I mean, you can grow crystals also at home in your cooking pot. You are just making a very saturated solution between water and salt. Then the water will boil, will go out as steam, and then you are getting your salt crystals. But in the industry, they are making these crystals out of a melt or by diffusion. A lot of different processes. And afterwards, you have to control these crystals, how good they are, and then you should know all these things. So, but now let us continue here, because we are far away from making crystals. Now we have the 6-fold axis, and you know by now what's going on. We can turn it 6 times. So, and you can turn it 6 times. That is then the example for a 6-fold axis, that is this hexagon. So and now I have examples for you. If they have not removed it, my friends here, they have. But anyway, we have here these two examples. I showed you this last time in class as well. Just give this around and then you can see if you are watching these crystals from the bird's view, yeah? Then you can see that the hexagonal symmetry. So and you can move and you can turn this then 6 times using one crystal, and then the crystal where you can produce such a tally here, and that is just the 6-fold rotation axis. So and now we are just checking how it looks like in 3 dimensions. We have here again the 1-fold, the 2-fold, 3-fold, 4-fold, and 6-fold. So now the 1-fold, we have now to move all the crystal faces. So these are the crystal faces. Yeah, this is a crystal face, this and this and this. So we have to rotate all the faces now 360 degrees that you can produce an overlap. Yep. So now we are making using the 2-fold axis. We have here just the letter A. So and now that is again the sign here. And we can move it 2 times that we can produce an overlap. Yeah? Then we have here the 3-fold axis. And again, we can move it 3 times now that we can produce an overlap. The 4-fold axis, we have here a cube, and we can move it around 4 times that we can produce the overlap. And last not least, your crystal, which you are just holding in hands, that is the hexagonal symmetry, yeah? 6-fold rotation axis. We can move the crystal faces 6 times within 360 degrees. So and now we have a combination of rotation axes. So here we have the perspective view, we have the rotation of the axis, we have the edge diagonal rotation, and we have the roto inversion. So here the perspective view, then we have the axis rotation. So this is the rotation just around an axis, and this is this axis here, and we can rotate this now, this cube, 4 times, yeah? So 4-fold axis, and we are just rotating it along this axis. So, but this we had by now. So, but now we are putting additionally the edge diagonal rotation. So that is the edge. What is the edge? This is the edge, yeah, here. So now we are making the edge diagonal rotation. So then you are rotating it along this axis, and then you have here, using this cube, not longer a four-fold axis like in the perspective view. Here we have then by edge rotation, we have only a two-fold axis, yeah? So, and now we are making the rotor inversion. So the rotor inversion, we are sitting now here on top of such a surface here, yeah? So, and here we have then not longer a four-axis and a two-axis, a four-rotation axis and a two-rotation axis. Here we have now a three-fold rotor inversion axis, yeah? Threefold, because we can turn it 3 times to produce an overlap. So, here we are sitting, what happens? Nothing happens. Now it happens something. Here we have the face. Now we are making a rotor inversion. We are just moving this surface here on the top, which is seen in red. That is a 120-degree rotor inversion. Then we are moving this surface downwards here. Then we have the next rotor inversion. Then we have a 120-degree rotation. So then we are making the inversion, putting this crystal surface to this side. So and now the next inversion, putting this crystal surface again to this side. So that was then the rotor inversion, and that is now the combination of your crystallographic system. You have one four-fold axis using this cube. That is from the perspective view. Then we have an axis rotation. I mean, that is the axis rotation, that was this one. That is just along this one, we have a four-fold rotation axis. Then we have the edge rotation, that is from this one, then we have a two-fold rotation axis. And then we have the rotor inversion, that is here from the top at the corner. There we have then a three-fold axis. So in putting these numbers then together, then you get a complete crystallographic symmetry. That is the combination of the axes. So now we have the mirror planes. So here between we have a mirror, and here we have the original motif, that is my hand, that is this one, and here we have then the reflected motif, yeah? So we are just, if we have here a mirror alongside, then we will just put one element from this side on this side, but it will become smooth because of the mirror. So how does this look like if we are having a one mirror plane, a two mirror plane, and a four mirror plane? So that is then a one mirror plane. Here we have the mirror, and then we are just moving the motif on the left hand, that is this one, on the mirror side, and you will get the identical one on the right hand side. Yeah? And here we have our mirror axis. Then we have two mirror planes. So then we have here the first one moving our object from this side to this side. Then we have here the next mirror plane, and then we are moving it to this side. Now this pattern shows the presence of two mirrors. Yeah? One mirror is here, and the other mirror is here. So these mirrors are perpendicular on each other. That means we have here 90 degrees. So, and here we have then also a twofold rotation axis, yeah? So, and then we have the four mirror planes. So, and then we are starting with the first mirror, that is here. Then we have the second mirror, the third mirror, and here the fourth mirror, yeah? So then we have a four-fold rotation axis as well, yeah? I mean, that goes then always together. So now we are going in 3 dimensions because crystals are made of 3 dimensions. We have a one mirror plane, a two mirror planes, and the 3 mirror planes. So that is then the one mirror plane. So in the one mirror plane is seen. This here is the mirror plane, yeah? So then we have a two mirror plane. Here we have again the mirror, yeah? And last not least, we have here a 3 mirror plane. So by now we have rotation axis and mirrors. This was so far to the mirrors or the mirror planes. Then we are going to the rotor inversion axis. So, and if you have a rotor inversion axis, then we have always this bar over your number, yeah? So, and that means here the 3 that is tetragonal and 4 is 3 is trigonal and 4 is tetragonal or cubic. So, and that I showed you before, that is the threefold rotor inversion axis that is here sitting on top. So, and now we are moving the crystal faces, or each cube face has an equivalent face generated by 120 degree rotation and inversion. All 4 equivalent body diagonals have the same symmetry. So and now you can move this here on the edge 120 degrees around, and then we have always the inversion through the center. Yeah? That is also important. The inversion goes always through the center. So, and here for a tetragonal system, we have here the four-fold roto-inversion axis. So, and here is just the same situation, but for the four-fold rotation axis, and there we have four triangles putting together. So, and I think here we can stop for today. Let me just check what is next. Yes, we will just repeat this tomorrow and then we will go to the center of the symmetry. So, and does everybody have this CD or this program now? Just go to Neil or I don't know, download it from the Moodle. I think he put it on Moodle.